Hello, so I'm going to be talking about durability today. Durability has always been a part of my career, as you mentioned. It just worked out that way. I didn't wake up and decide, durability is really my calling in life when I was 12. So I started off in Unix operating systems internals and primarily file systems. And then about 15, 20 years ago, I moved into database storage engine systems with both SleepyCat and BerkeleyDB and WiredTiger. And actually, database storage engines are not very far off from operating system internals. Database storage engines need to deal with caching and blocks and pages. And so there's a lot of overlapping concepts. I have been at MongoDB for almost 4 years. I came as part of the WiredTiger acquisition. When you combine the 5 original engineers from WiredTiger, we have over a century of operating system internals and database experience. By the end of today, you are going to be sick and tired of hearing of ACID. But in case anyone was not at Keith's talk, I'm also going to be talking about the basic transactional concepts of ACID and what do they mean. The A in ACID stands for atomicity, as you have heard over and over. All the operations of a single transaction have to be performed as an atomic work unit. The canonical example is a bank ledger. Your financial institution runs far more complex software. But if you think of a bank transfer, if you're moving $10,000, withdrawing it from account A so you can deposit it into account B, and the system crashes in the middle of that transaction, when the system restarts, you need to know whether or not the money is still in account A or it made it into account B, but it can't have been lost somewhere in the middle. MongoDB uses WiredTiger's transactions in the case of collections and indexes. So when you insert into your collection, you've got to make sure that your data atomically also gets inserted into any of the index files that it needs to go into as well. The C in ACID stands for consistency. The database needs to move from one consistent state to another. And as Keith mentioned, that is defined by the rules. In relational systems, that is typically defined as things like constraints or triggers. So for instance, your database may require that a date is later than some other date in your data, or that some value falls within a certain range. The I in ACID stands for isolation. Concurrently running transactions, how do those transactions see each other's data, and what do they do? So WiredTiger offers various isolation levels that can be used, and those various levels have other trade-offs. One isolation level is read uncommitted. A transaction running at read uncommitted can read the uncommitted data of a concurrently running transaction. That's great. You can see the latest information about a piece of data. The trade-off you're making is if that other concurrently running transaction aborts, that data you read can change and revert back to some earlier value. It can disappear entirely. There are other levels such as read committed and snapshot. MongoDB uses snapshot isolation levels, but there are trade-offs for all of these different levels. And the D in ACID stands for durability, and that is going to be the focus of the remainder of my talk. The most common implementation of durability for transactions is a write-ahead log. And that is, in fact, the type of subsystem that WiredTiger implements for its durability story. And similar to isolation levels, durability has different durability choices that you can make, and there are trade-offs that go along with each of those. I'm going to be going through those different levels in detail today. And I do want to make clear that I am talking about WiredTiger on a single node. This is not the replication oplog. Replication uses the durability of WiredTiger on a single node as a building block and foundation for building the system above WiredTiger. And the transactions I'm talking about in WiredTiger are not the user-level transactions coming out in 4.0. These are the transactions that MongoDB has used internally since 3.0. So the durability modes that WiredTiger provides, there are 3. The first one is known as in-memory mode. When you want to store a record that reflects the modifications made within a transaction, we first write it to a memory buffer within WiredTiger, and then we can return to the caller in in-memory mode. Then we have a second mode that we call write no sync. And what that means is that we write to the WiredTiger memory buffer, and then we write that to the operating system buffer cache through the write system call. But no sync means we're not syncing. We're not going all the way to disk, but it is in the operating system memory itself. And then third mode that we have, we call full sync mode. It does what you might expect. We write to the WiredTiger memory. We also write it to the operating system buffer cache. And then, once the write completes, we flush all the way to the disk. And of course, as you may expect, there are trade-offs between these different durability modes. Here's a very simple graph. Not surprisingly, in-memory mode is the fastest by a lot. The worst performance, also not surprisingly, is full sync mode. And write no sync is somewhere in the middle, but you are crossing the user kernel boundary and writing into the operating system memory, so it's a little bit closer to full sync than in memory. So let's explore the durability of data with each of these 3 modes in the face of a failure of either the MongoDB server process or a full system crash. With in-memory mode, there actually is the potential for data loss, either with a process crash or with a system crash. In write no sync mode, since your data has been written into the operating system buffer cache, you're protected if the MongoDB process fails because the operating system will still have your information when it comes back up. But there still is the potential for data loss on a full system crash on a power cycle. And in full sync mode, your data is always recoverable in either case, in either sort of crash. So now that you know what durability is, why is it important? Why do we care? For me, it answers this question. What keeps me up at night? The answer to this is different for everyone. A data scientist doing genome sequencing will have a different answer than a surgeon, than a security expert and cryptography. What is it in your job that keeps you up at night? For storage engineers, we have to consider situations like this. We really, really want to help you, our customers, avoid this. We really do. So for a storage engineer like myself, I can sum up what keeps me up at night in 3 words. Losing people's data. It is what we think about all the time. Sleep is important to me. I hope it is to you too. So what can we do to allow ourselves to sleep better and let you, the customers, also sleep better? So with durability, we're making a promise to you that we're keeping your data stable and consistent. And remember, this is on a single node. When the replica set crashes, when the power goes out, what are you coming back up with when you restart? We're making a promise to you that if we say your data is stable and written, that it really is. And not only when we say your data is stable and written, great, it's out on a disk somewhere, but when a crash happens, because it inevitably will, we can make it come back. We know how to find the data. We know how to make it consistent again with the rest of the system. We can make it usable to you. So after a restart, after a crash, we can recover your data for you. So to make sure we keep our word, that if it's stable, it really is, we run a lot of testing all the time. We have specialized crash recovery testing that is running 24/7. It is running random numbers of threads. It is having other processes kill and crash the machine, power cycle, killing the processes. It knows exactly what data should be there when it comes back up, and it runs in all the different modes that I mentioned already, so that if there ever is a failure or a change in our system that we've made that introduces a failure in these tests, it is a top priority job to figure out what went wrong and fix those problems. So by running these tests, we gain a lot of confidence in our code. When they run for weeks or months at a time without a single failure, we're feeling pretty good about it. We really do think long and hard about the durability guarantees that we're giving you. We do pay close attention to things that are going on in the industry, in particular any operating system issues or file system issues that come to light. And in fact, one came to light recently that I will discuss later that made us make a change in our system and backport it to earlier releases just recently. And so we really do think about how new features impact durability and the guarantees we can make to you. So we think long and hard about this so that you don't really have to. Have you ever wondered what really happens to your data? Let's consider all the layers of the system all the way down and how they fit together. At the top layer, we have your user applications. You're doing analytics, you're doing IoT sensor data gathering, you're doing website content, all those cool things that are wide and varied and really interesting and really cool, and people get to use it every day. The applications then talk to MongoDB via the query language layer or any of the native native language drivers that MongoDB provides. Then those native drivers talk to MongoDB with the document data model, and they're talking to the MongoDB process. That's also providing ancillary services such as security and other management services. And within MongoDB, there is a storage engine API layer, and underneath that, the various storage engines that are supported under MongoDB, one of which is WiredTiger. So let's expand the WiredTiger storage engine box. At the top layer, we have the MongoDB storage engine API, which is within the MongoDB source tree. And underneath that, there's about 14,000 lines of code that MongoDB uses to, we call it the glue layer or the integration layer, that talks the WiredTiger C API in MongoDB itself. Then underneath that, we have the actual standalone WiredTiger API, WiredTiger library that has a C API, which is what MongoDB is using in the glue layer. WiredTiger also has Java and Python APIs, but MongoDB just uses the C API. So in WiredTiger, we have the user-facing APIs in the form of schema and cursors. Schema refers to the operations that affect the tables, the collections and the indexes. So you can create tables, you can drop tables, you can rename them, and those sorts of things. Cursors refer to the operations of manipulating the data within the tables. So you open a cursor, and you can iterate over it to read your data. You can insert and update, and all those sorts of things. Beneath the cursors, we have the row store and column store portions of WiredTiger. MongoDB uses the row store, and that's how we manage your data within WiredTiger. And below that, we have the WiredTiger cache. Anyone who was here for Keith's talk, that is where the MVCC list of updates are stored. So the WiredTiger cache is really the content of all those different versions of data WiredTiger has to keep in order to serve various read requests from transactions that have different IDs or timestamps. And then when the cache is full, when data needs to be written, our block manager writes out to the database files. Those are the table files of your databases. Then on the right side, we have the transaction subsystem. Again, this is the WiredTiger transaction subsystem that has existed since day one, and MongoDB uses that. The transaction subsystem deals with snapshots, so we get a consistent view of the data. And the transaction subsystem also writes into the logging subsystem in the form of the write-ahead log. In this talk, the logging subsystem refers to the write-ahead log, also known as the journal, and I will be using logging, log, journal in various forms throughout the talk. They all mean exactly the same thing. And so the transaction subsystem goes out to the logging subsystem, and those write log files on disk. So today's talk is going to focus on the only two paths out of MongoDB and out of WiredTiger that go to the disk. That's what I'm going to be highlighting. So when people decide to save their data, they just assume that it works. But what really happens here? Durability is really many, many layers of trust. If you think of it as a human pyramid, every person in that pyramid is key. If anybody collapses and falls down, the whole thing is going to collapse. Everybody has to do their job. I prefer to think of this as the old myth of regress, as turtles all the way down. So let's say you, the user, has some important data. You really want to make sure this important piece of data is stable when you insert it into your MongoDB database. So in this example, because I'm primarily focusing on single node, let's assume you give a write concern of jtrue. What does that mean? Here's the contract that MongoDB makes with the user when you give a jtrue write concern. The write concern describes the level of acknowledgement requested from MongoDB for a write operation. If jtrue is set, the user requests acknowledgement that the MongoDB instance has written that to the on-disk journal. So MongoDB is promising to you, the user, that when you set jtrue, it will be written to the journal. So let's look at the write concern code for MongoDB. If the mode is journal, we call a method wait until durable. In the WiredTiger storage engine code within MongoDB itself, there's a wait until durable method. When the journal is available, we will call a WiredTiger API called log_flush, and we will pass in a sync equals on configuration string. So MongoDB uses the WiredTiger API function called log_flush, and let's see what that documents as its contract. The contract that WiredTiger makes with users of the WiredTiger library, of which MongoDB is that user in this case, for log_flush, it says, we will forcibly flush the log and wait for it to achieve the specified synchronization level. When that level is set to on, it forces the log records to be written to the storage device. So now let's wander through the layers of the WiredTiger source code. When we come into the log_flush, if we match the on string for our configuration string, we set a flag called fsync. And then we call an internal WiredTiger log_flush function. In that function, if that flag is set to fsync, we call another function that forcibly syncs the log. The force sync function does what you'd expect. It calls a wrapper we call WiredTiger fsync, which wraps our various operating system layers of system calls. This code that I'm going to show you is all POSIX based. And so we call into the POSIX sync function that is still within WiredTiger, and that makes the actual system call fsync. So now let's see what contract and POSIX documentation says about fsync and the contract we make from that. This is from Linux, and it says, fsync transfers or flushes all modified data of the file to the disk device so that all changed information can be retrieved even if the system crashes or is rebooted. The call will block until the device reports that the transfer has completed. Now, that operating system issue that I mentioned earlier comes into play here. It recently came to light, actually, that Linux only guarantees in fsync the data written since the previous fsync call. WiredTiger, originally on an error from various system calls, including fsync, will retry the operation. And so we were retrying an fsync call on an error. But with Linux not guaranteeing earlier data was written, only data since the most recent fsync call, we couldn't guarantee that the earlier data prior to the error was actually written to disk. So now, instead of retrying fsync, WiredTiger has to crash, and it's a panic situation because we cannot make that guarantee to you anymore. So here's a version of Linux code that you can find online. The top line is the actual system call interface once you cross the kernel boundary. So we have the fsync system call. That calls into the VFS layer. VFS stands for Virtual File System, and that is a layer within the operating system that wraps different file systems underneath it. So in this particular example, the wrapped file system is XFS for this code. The XFS code then calls into the block device for that file system. And the block device code then formulates an I/O request to the device driver and waits for the response, and then it will return to the caller. So the operating system is now trusting that the device driver will not return until it has flushed and written the data. And then we have the device driver layer, which is the final piece of software to the hardware. It's very device specific and disk specific, so I did not pull up any example source code for device driver. And then finally, at the bottom layer, we actually have the hardware. The device driver is trusting the hardware that when it says, flush this, and I'm waiting for you to tell me it's done, that the hardware will do what it was told and then not return until it's done. But hardware can sometimes lie. Hardware itself also does its own data caching within the hardware itself, and most of those are battery backed up. But there are, in fact, some disk systems that do their own caching without battery backup. So if the hardware lies and says, yep, I've got your data, and a power crash happens at that time, and it's only in the disk's cache, not on the disk itself, there is a potential for data loss. But those are rare systems. But you may need to be aware of device caching and might need to turn that off. So let's summarize the path we've drilled all the way down from the user to the hardware. The user decides that they want some some data stability. We need to have some assurance our data is good. So the user is trusting MongoDB with the JTrue write concern. MongoDB's storage engine is now using WiredTiger's log_flush API and is trusting WiredTiger to do what it says it's going to do. WiredTiger is trusting the operating system and doing its fsync call and trusting that the operating system is going to sync the data. The operating system is trusting the device driver. And finally, the device driver is trusting the hardware. And that is how we go all the way from the user wishing for stability down to the disk itself. So now let's talk about the specifics of WiredTiger durability. Let's re-examine in detail the two paths out of WiredTiger to the disk. WiredTiger offers two forms of durability. Durability is not quite the best word here because what I've been talking about durability right now is explicitly fine-grained durability. but we offer what we call coarse-grained durability in the form of checkpoints. Checkpoints are periodically run, and that period can be measured in minutes, which is why it's called coarse-grained durability. And fine-grained durability is the write-ahead log. MongoDB uses both forms of durability working together, and I'm going to examine and make it clear to you why we need to do that. So recall our structure of the WiredTiger library. The only path out of the library to your collection tables is through the WiredTiger block manager. And that is the path that coarse-grained durability takes. Let's examine what happens with checkpoints. So a checkpoint occurs whenever the checkpoint API is called. It is an at-will call. And MongoDB has an internal thread that, in fact, calls the WiredTiger checkpoint API. What a checkpoint does is it opens a snapshot transaction internally. And then it can write out all dirty data that's in the WiredTiger cache that is committed as of the time that snapshot transaction was opened. So the snapshot transaction can only see already committed data within the WiredTiger library, and it knows via the cache which is dirty and which is clean, and it can write that out. So now let's take a look at what happens inside on disk and in the WiredTiger cache. We have an empty system, and we create a collection. The file itself gets created, but there's not yet any data. So let's say we have a fruit collection, and now we insert some data. This data is actually going to stay in the WiredTiger cache until some external force causes it to get written out to disk. So we add some data, and now MongoDB wants to take a checkpoint and save the data. So MongoDB does this with the checkpoint library API call. And WiredTiger will write that to the file on disk, and the data is now safe on disk. Now we insert more data. We insert orange and pineapple, and a crash happens. Let's see what the system looks like on restart. When WiredTiger restarts and reopens collection tables, only the most recent checkpoint information is available, and that's what it restarts with, if one exists. It may not. So after we restart, the collection contains the original data of apple, banana, and cherry, but the additional data of orange and pineapple has been lost. That's why it's coarse-grained durability. It is coarsely at whatever period we were taking checkpoints. So let's contrast this to what happens if we don't do any checkpointing at all and instead use the WiredTiger write-ahead log. Recall, the only path to the writing of the log files to disk is via the write-ahead logging system, and that's called from the transactional subsystem in WiredTiger. Instead of an API call, the log is a property of the WiredTiger database as a whole, and so that has to be configured when the WiredTiger database is first created. A WiredTiger database is the collection of all MongoDB databases and collections. So a WiredTiger database is generally a superset of all the different MongoDB databases you can have. And in MongoDB, enabling the WiredTiger write-ahead log is the journal or no journal setting that you can give. And when configured, every transaction will make a recording of its transactional modifications to the write-ahead log prior to making that visible to other threads on commit. So let's revisit our example. Again, we start with a fresh system, but this time we have enabled the write-ahead log. We add some data to the collection, and each transaction adds to the write-ahead log before the data is visible, and we return from the commit call. So we add our apple, we add banana, we add cherry, we continue adding, we keep adding our extra data orange and pineapple, and now we have a crash. So recall, when we restart, we will start with the latest checkpoint if one exists, and then with the log enabled, we will recover and replay the write-ahead log. So in our example, when we restart, our collection is empty. We never did a checkpoint. There's no data in the table itself. But recovery will replay the write-ahead log. So when recovery runs, it will read each of the different log records, and it will reinstantiate all that data into the WiredTiger cache. And recovery itself will always do a checkpoint to the table when it completes. So when WiredTiger startup completes, then MongoDB startup can complete. And when you start up your application, all of your data is actually there for you. So we have solved the problem. We have not lost your data here. But this works great in this tiny example. However, I'm sure you're thinking, this is not sustainable once you've got thousands of collections and indexes and weeks or months worth of updates. And you would be correct. It would take forever to replay this all the way from the beginning. So now let's consider what we get when we combine both coarse-grained durability and fine-grained durability in the form of both checkpoints and logging. We're going to get faster recovery. We're going to get less disk usage, and we'll really get the best of both worlds. So again, we start with a fresh collection. We add our fruit, one transaction at a time. And now we take a checkpoint. Similar to last time, the data is written to disk, and we also write a marker into the write-ahead log, indicating that a checkpoint has occurred. And now we add our new data, and now we crash. So let's see what we have on restart. As you'd probably expect, this is the state of our system on restart. However, recovery knows that it only has to replay content since the previous checkpoint. So it only has to replay those last two operations. So we recover those last two operations. Recovery writes a checkpoint, which gets all the data into your collection for you on startup, and all the data is there. So to summarize how checkpoints and logging work together, we get faster recovery time. Checkpoints bound your recovery time. The more frequently you checkpoint, the less records you'd have to replay on a crash and restart. The less frequently, well, then you'd have to replay a little more. But you, at least by taking checkpoints, you take some points in time where you can start recovery from. You have less disk usage. Log files are not one giant file that keeps growing forever. We have multiple files that are configured size. In MongoDB, they're 100 megabytes. And when we've written that much data, we transfer to a new log and close the old log. So recovery will never, ever visit a log record prior to the most recent checkpoint. So we can archive or remove any log files earlier than the one containing the most recent checkpoint record. So we can use less disk space for you. And you still retain the benefits of fine-grained durability. We can recover your data that has been written since the most recent checkpoint. We can recover that intermediary data for you. So now let's revisit how MongoDB uses WiredTiger transactions and logging to guarantee your durability. The Transactions API in WiredTiger has always existed, and MongoDB has always used it to make sure collection and index operations and other things are atomic and consistent. So the only way into logging is via the transaction subsystem in the form of commit and checkpoint. And as write-ahead would apply, we call this prior to the commit, making its resources available and visible to other threads in the system. So the example I showed flows really well in the write-ahead log, but it's subject to the durability modes that I mentioned earlier. So let's review those three modes. Depending on the nature of the crash of my example, it really implies that I was talking about write no sync or full sync mode, because if the data only existed in WiredTiger memory, it could have been lost. So in memory, which is in fact both the WiredTiger default and the mode that MongoDB uses, there seems to be the potential for data loss. And I know you're thinking, MongoDB uses the least durable form of these modes. How do we resolve the fact that MongoDB is making guarantees to you? And the single answer about why MongoDB uses it is performance. It is the most performant by a lot. I mean, just copying some bytes from one chunk of memory to another is much faster than crossing into the kernel boundary. So while in-memory in WiredTiger doesn't force it out to the operating system immediately, it also doesn't sit there forever. Any one of several things can force the log record out of WiredTiger memory and into the operating system at any rate. The memory buffers are fairly small, so as multiple log records keep coming in, we will fill that memory buffer and write it out and start filling a new memory buffer. So that will cause it to get written. Any later log record or call that needs durability guarantees will force all earlier ones to be written out to disk. And in the case of an idle system, where you did a write, it was written into memory, and now your system goes quiet, that will not languish in that memory buffer. WiredTiger has an internal thread that will write that out every 50 milliseconds, 20 times a second. So depending on your tolerance for risk, sometimes the in-memory mode can actually behave a little bit like write no sync mode with some 20 times a second. So MongoDB uses the in-memory mode for performance. It's got a lot of transactions going on internally to WiredTiger going on at the same time. Many of those do not require these durability guarantees. So we can give fast performance for a lot of update and insert operations going on. And when an operation does require that durability, MongoDB can use the log_flush API to force out those records and make the guarantee for that operation that requires it. So to reiterate my feelings on durability, it's cool stuff. It's interesting. As Keith mentioned, storage is hiring. I hope you enjoyed learning about it. We solve a lot of interesting problems. And we do take the responsibility of keeping your data durable very seriously. And I do really sleep well at night. I hope you do too.